Welcome to this first lecture on the NPTEL course on basic building blocks of microwave engineering. Now, the theme of this first week lecture will be the mathematical model of microwave transmission. You know that from the source the electromagnetic energy propagates. Now, it propagates through various channels and then reaches its destination or receiver or sink. Now, we will model first this first part, the transmission, and in that theme the first lecture today that we will address is concept of mode in microwave transmission. Myself Amitabh Bhattacharya, ENEC Department, IIT Kharagpur. You can reach me in my email here. Now, let us see if we look at the universe if we look beyond our territory, that is Earth. You see, we see so many stars, so many galaxies, etc. Now, do you know that all of them, they radiate either light, that is why we are seeing them, or they are also radiating electromagnetic radiation. And there is one Nobel laureate, Michael Booth, who measured and found that in Earth everywhere we have something like 2 degree Kelvin of microwave radiation always, that is the background microwave radiation. So, always we are getting bombarded with microwave radiation, we are living with it. Also, you know, sun emits solar flare, that is why when the solar flare reaches Earth, it is not always, but sometimes when it reaches, solar flare is different from the normal light. So, solar flare when it reaches, all the activities in communication etc., they get stopped. So, ISRO has a calendar, they keep track of when the solar flare reaches us, and that is why they notify, and that time all our satellites etc., they stop working, because solar flare creates magnetosphere and that creates huge electromagnetic field. All of you are familiar with this sight. In rainy season you will see lightning. Now, you see a lightning striking the earth, it is a huge source of electromagnetic emission due to the high potential, high static charge potential. There is air gets breakdown, and that is why you see that due to that breakdown the light gets produced, the sound gets produced. Now, sound is not electromagnetic energy, but this light is, and that reaches earth. It, you know, if you try to receive this energy, you will get killed, but that energy comes here when it is not striking neither a tree or anything, but in the whole atmosphere you are pervaded with these terrestrial lightnings. Then you see satellites, natural satellites in the right side, in the left side the man-made satellites, huge number of them, all of them are communicating with earth. By what? By electromagnetic signal. So, you are always getting signals from them. Then you see, let us see a typical family, how we are surviving today. There are Wi-Fi's, that is emitting electromagnetic environment. You see satellite, that is doing that. You see TV, that is doing that. You see mobile phone, nothing but electromagnetic radiation. You see a ground station, satellite ground station. You see your tab or pager something. You see mobile phone. You see electric towers. You see so many devices. So, we are living with it. Now, we need to understand this environment if we want to master this technology. So, let us see that electromagnetic spectrum. You see, starting from a soccer field, that large size of wavelength to water molecule etc., all are electromagnetic environment. But we will not talk with this whole spectrum. Our microwave technology means, you see, we have noted that radio waves, you can see that up to the soccer field to roughly the baseball size of wavelength, baseball diameter wavelength, that is radio waves. But after that, from baseball to, let us say, this a point dot, that wavelength type of radiation, the radiation for which wavelength is that long, that is denoted as microwave. As you can see that this is the zone of microwave. So, here we will mainly talk with that, and just beyond that you see, if we go still further in wavelength, that means still higher in frequency, you can appropriately see from here we are reaching terahertz radiation. Now, microwave radiation, as the technology is progressing day by day, it is going towards terahertz radiation, and similarly this terahertz radiation also coming day by day beyond. So, almost these two technologies are getting merged, or I think when you people will be finishing your career, that time it will be completely merged. So, we need to understand this technology, and for that this following lectures will help you to understand the basics of that. Now, you see, from all this field, if I look at any environment, actually we are doing in a particular place, we are trying to map the electromagnetic field distribution, and it came something like this. This is a color plot. So, you see the red ones, they are the maximum things, maximum radiation level, electromagnetic radiation, then it is coming down. It is actually the radiation density, electric field radiation density at that point. And you see that gradually it is going down. Obviously, this blue etc., those are very low, but you see there are various types of these field distributions are possible. Now, the question is, if we want to understand and microwave engineering, then we need a model. That is the basic task of any engineering, that when we try to analyze or we try to understand something, we make a model. So, that is why we say that if you want to understand, you want to design, you want to analyze any practical system, you want a mathematical model. So, for microwave transmission system also we want model of this EM signal. As I shown you just before, that if I want to have what is happening, I need a model, mathematical model of EM signal. Now, EM signal again I have listed for your convenience from that spectrum graph, that you know X-ray, light ray, infrared, microwave, TV, radio, radar, mobile telephone, landline telephone, everything comes under EM signal. Out of that I can say that microwave, TV, then radar, then somewhat mobile telephone, these are in our microwave zone. So, the question is, do we need for each of these type of signals, because each of signal will be different, that is why they are coexisting at any place, all these signals are present. Now, that means if I want to understand, do I need a model for each of these signal? Then my job is just remembering all those models, it will be a huge task. So, fortunately it is not so. So, now all these EM signals, they obey Maxwell's laws. All EM signals, light, you know, Sir Jesse Bose, he proved that okay, light is indeed a form of electromagnetic radiation. So, let us see light and mobile phone signal. Now, both can be, light can be seen, but mobile phone signal cannot be seen, but still both of them obeys Maxwell's equation. There are various solutions of Maxwell's laws. Light signal is one such solution, mobile phone signal is another such solution, radar signal is another such solution, etc., etc. So, do I need to understand all these? So, that means let us make a set of all EM signals. So, one can make a set of all such EM signals. Are all these signals independent? If it was, then we had to understand all these signals, but no. Answer is no. Fortunate for us, there are a minimal number of independent solutions such that all EM signals can be expressed as linear combinations of them. So, you see that though there are various solutions, but they are not independent, there is a minimal list of independent solutions, and all solutions are linear combinations of them. So, that we are fortunate, and these minimal number of independent solutions are called modes. So, you see that people generally say that modes, what is a mode? Modes are solutions of Maxwell's equation. I say it is partly true answer, because any electromagnetic signal, as I said, that light signal or a microwave signal or a radar signal, that is also solution of electromagnetic signal, but all signals are not called modes. Modes are the number of independent solutions, minimal number, in which we can express. Now, those who are familiar with set theory, they understand that basically this we can call as a basis set. You see, if I have a set of signals, then there is a minimal number of sets, minimal number of elements of that set, in terms of which I can express all the elements of that set. That set is called the basis set. Like for electrical signals, Fourier proved, the famous Fourier, by his Fourier theorem, he proved that okay, you can take a exponential basis set to express all sorts of electrical signal. That is why today we take either cos or sine or sinusoidal signal, we analyze that and say okay, we know all the signals, because all the signals can be linearly expressed like that. So, Fourier took a basis set. Okay, there are other basis sets also possible. Now, modes, its precise definition is modes are mutually independent solutions of Maxwell's equation, such that every possible electromagnetic field configuration can be expressed as a linear combination of the modes. So, for our learning purpose, if I understand the field distribution in a mode, then I can construct any signal. So, my model requires that what will be the this modes field distribution. So, let us come that obviously when EM signal is produced, there needs to be a source. That source may be near the signal, because electromagnetic signal propagates as a wave. So, when I am looking at the signal, the source may be near, may be far away, but to start with, one kind of source is a point source. Now, point source is actually an ideal source, like the concept of point in geometry, which you know that it is an abstraction. Similarly, ideal point source, it is an ideal source, it is an abstraction, no real source is a point source. All distant stars, as I was showing in the first slide, that you see so many stars, but they appear to be as a somewhat, not point something more, but if we are really far away, then all distant stars appear as point to our eyes. But if we go closer to the star, what we see? We see the star, it is a huge size, there are variety of contours, there are mountains here, there are rivers here, there are caves here, craters here, etc., etc. So, any far away distributed source of EM field is considered as a point source. And if the source is nearby, then we know what is its contour. So, we can say that it is summation of all those point source. So, any distributed source nearby, we call it is summation of point sources. Now, point source, it radiates equally in all direction. This point, it does not have a preference of radiation to any particular direction. Again, I am reminding that no real source is a point source. Every real source has a preferred way of radiating, a preferred direction in which it radiates more than others. But when we idealize or when we learn thing, point source we define as which radiates equally in all directions. So, that means that the origin there is a point source. So, in all possible directions you are giving a wave, can be seen equally bright in all directions. You have not seen anything till now which does like that, but ideally you can say because if you observe a distant star, now in the earth if you move reasonable distance, suppose in a region etc., you do not think that there is any change in that. That means that is as a to you it is appearing as a point source. But if you really travel far, then you are traveling much, so something, suppose from northern hemisphere to southern hemisphere if you come, then you see that okay, that is changing. So, we can say that energy is coming equally in all direction from point source, and people have found out the solutions for that. It has been seen that emits spherical waves in all directions. So, if you are a center of a sphere, then the energy is equally going along larger and larger spheres and coming to you. At a particular distance from the source, if we connect all the equal amplitude and equal phase points, that means whose any field, electric field or magnetic field, its equal amplitude and equal phase points if you connect, then the locus becomes a spherical surface. So, its phase front is called spherical. So, that means when any point source is emits electromagnetic signal, then at a particular distance, if we connect all the equal amplitude and equal phase, that means equal signals where they are, then if we connect that, that becomes a spherical surface. That is why we say that point source emits spherical waves in all directions. Now, at a large distance from the source, you know that sphere, if you go on constructing larger and larger spheres, now very large sphere at a particular place, you will see that the spherical surface is almost becoming a planar surface. So, that is why we are saying that at a large distance from the source, this spherical surface becomes approximately a plane. Then these waves are called plane waves. Now, we will see plane waves, and or you have already seen plane waves in EM theory. Plane waves means in that plane there are electric field vector, magnetic field vector, they do not have any variation, they are constant over the plane, that is called uniform plane wave. First plane wave, that all equal amplitude and equal phase points, they are plane, and then if you have uniform plane wave, which is a variety of plane wave, where they will have there is no variation in that plane of the amplitude or phase of that thing. So, that plane waves you have seen already, its solution you have seen in a thing, it is that cos omega t minus kz type of thing, or e to the power minus j kz, that thing. So, for plane waves you have also seen that electric field vector, magnetic field vector and direction of EM energy, propagation of EM energy direction, that form a right handed orthogonal triplet. This you have already seen. So, for plane waves this is true. Now, we see the second type of or another type of source. Instead of point source, suppose we have, all these are abstractions, but it will help you to understand what is a source and how it radiates. Suppose we have an infinite sheet of surface current source, that means a whole plane where we have a one directed surface current, it is called sheet of surface current source. So, here we have taken that in the z is equal to 0 plane, the sheet of surface current source is lying. So, what we have written that not only point sources, some other sources also can produce waves whose electric and magnetic field vectors both are orthogonal to the wave propagation direction. So, consider an infinite sheet of conducting surface current density, let us call that surface current density Js, and consider, obviously since we are talking of electromagnetic field, that means this is not a DC current, it is an AC current, that is why I am writing consider time varying Gs. The surface current density is time varying, it has a time function, it is dependent function of t, and also for simplicity I have assumed that it is in the xy plane, it is x directed. It can lie in any direction, but we can orient our xy thing, so that for simplicity it becomes x directed thing. Now, since you see this source, this source, it is an infinite source, though my drawing does not represent that, but in xy plane it has an infinite variation. Actually, there is an x here, you see this is x, though I do not think it has mixed with the contour. So, in xy plane it is infinite. So, since it is infinite, and you know that if there is an there is an conduction current, that means in that direction there are the electric field also. So, if Js is in x direction, obviously the electric field will also be in the x direction, but since there is no variation in the whole infinite plane in either x or y, please remember that it may be x directed, the current is x directed, electric field is also x directed, but they do not have any variation, because the whole source does not have any variation in the neither x or y direction, but it definitely has a variation in the z direction, because suddenly it is here, just at z is equal to 0 minus it is not there, at z is equal to 0 plus it is not there. So, it has a variation only in the z direction, but in x or y direction it does not have any variation. So, this type of source. So, due to the discontinuity, as I was saying, in the z is equal to 0 plane, there will be EM waves propagating away from the source in plus minus z direction. This you will always remember, that if there is any source has a discontinuity, that it is suddenly there and then not there, then it will radiate. So, it will radiate obviously in plus minus z direction, and already we have discussed that the electric field is x directed, the movement the propagation of wave or propagation of energy is in z direction. Now, let us put the, you all know, boundary conditions of electromagnetic fields. So, boundary condition at z is equal to 0, if we apply, we know that what this is saying, you know, n is a normal vector. So, n cross E2 minus E1, that means what? Tangential component should be continuous, tangential component of the electric field should be continuous, that is the boundary condition 1 of electromagnetic field. Similarly, the tangential component of magnetic field n cross H2 minus H1, that is discontinuous, and the amount of discontinuity is the surface current density. It is the second boundary condition of electromagnetic field. In our this particular case, n is the outward normal. So, n is positive Az directed, and E1 H1 we are calling, it is the electric and magnetic field in region 1. Region 1 we are defining as Z less than 0, that means below the current sheet, and Z greater than 0 is above the current sheet, where the fields are E2 H2, that is why we have written this boundary condition. Now, to satisfy this boundary condition, n is Az. So, Az cross E2 minus E1, we know that E2 minus E1 will come, then the H2 minus H1. So, Az cross this is equal to some Ax component. So, obviously, it says that H2 and Hy, they must have y component, simple mathematics. So, we can write the fields as E1 phasor, that will be equal to in x directed, and then we assume some amplitude A. First we assume, since H1 is y directed, so H1, let us assume in the lower one, you see, to satisfy that equation, in lower one it will be minus. So, minus Ay, A is some amplitude, then we know that the field is propagating in z direction, means its variation will be to the power j k naught z, and E1 and H1 we know that always they are related by the wave impedance. In free space it is propagating. So, eta naught, the intrinsic impedance of free space. So, there E1 will be like this. Similarly, at z greater than 0 we can write H2 and E2, some other constant B amplitude and some other constant B here. So, A B needs to be found out. So, to satisfy boundary condition 1, we get A is equal to B. To satisfy boundary condition 2, we get this. So, solving we get that A and B, their values we get. So, by that we can find out that there is an electromagnetic field. So, we see that it also produces surface current, infinite surface current, that produces an electric field. So, that you can have the propagation in the plus minus z direction. Now, so in this case also you see that we have electric and magnetic field vectors, both are orthogonal to the wave propagation direction z. So, you see that E and H, they are all lying in xy plane, the wave is going in z direction. The E and H field does not have any component in the propagation direction. This is the first mode that we introduce, that if and both the electric and magnetic field, they are lying on the transverse plane, that means transverse to the direction of propagation, then we call that as TEM mode or transverse electromagnetic modes. To any propagation direction, one can draw infinite number of perpendiculars. That means, if we have any direction to that, you can draw a perpendicular, draw a perpendicular. So, all these are perpendiculars to it, you can have many, because with this I can have this as a perpendicular, with that I can have other perpendiculars also. So, but all these perpendiculars, they will lie in a plane, that is in this transverse plane. So, this plane, so there any line is perpendicular, and now electric field vector can lie along any of these infinite number of perpendiculars. Now, in the transverse plane, we can always find, in a plane we can find always a couple, another perpendicular, two perpendicular couple we can always locate. So, along the perpendicular to the electric plane, we can always locate another perpendicular, which is a magnetic field vector. So, this TM wave is a mode. In a guided structure, like in normal coaxial transmission line, this mode propagates. In unguided fields, that means when we radiate by antennas, then at a far up distance from the antenna, this becomes a TEM wave, that we have discussed, that from the stars when we are far away, they become plane waves. Plane waves are an example of TEM mode, but reverse is not true. Apart from plane waves also, there are many examples of TEM wave field distribution. So, any antenna is a distribution of point sources. So, at a far off distance from the antenna, the radiated field show TEM mode field distribution. This is the TEM mode field distribution. You see that it is in a coaxial line, we get this type of distribution. Here you see that we have so many all the this is only electric field I am showing, it is entirely in the xy plane, the propagation is taking place in the z direction. So, it is the magnitude is changing, as you see from the color plot, but it is changing. So, you see if we look in the z direction, this is z direction, in a transverse plane there is no z component. So, this is an example of a TEM field distribution. Now, let us see an infinite line source. So, this z directed line source, instead of a infinite sheet of current which produces TEM waves, we are now seeing an infinite line source. So, the source is a line, infinite line, IL let us call. Now, in the z plane will be the transverse plane to this. Consider an infinitely long conducting line current source. No magnetic field can exist along this infinite line source, that is Biot-Savart law or Maxwell's law, that if you have a current source, magnetic field is always perpendicular to that. That means, along this line source there is no magnetic field component. So, where is the magnetic field vector then? It should lie along the transverse plane, that means that z is equal to 0 plane. So, magnetic field should lie there. Now, electric field vector can be anything, but we have already seen TEM case. So, we say that there both the electric field vector and magnetic field vector was in the perpendicular plane. Here we say that since we are trying to see whether another mode is possible, another solution of Maxwell's equation, another independent solution is possible. So, that is why we are checking that electric field vector should not be lying entirely in this plane, because if it lies entirely in this plane, that is a TM case. So, if it is in this plane, we are going back to the TM case. So, we are trying to see another fundamental variety of mode. So, electric field vector should have a component in this transverse plane as well as some component along the line source direction. So, this mode is called transverse magnetic. That means, magnetic field is entirely in the A plane, and if you do the mathematics, this line source gives that TM mode, it does not give any TM mode. The energy is propagating. How energy is propagating? If you consider that, considering that line current as an axis, if you consider a cylinder, throughout that cylinder surface the energy is propagating. These waves are called cylindrical waves. Their field distribution is TM field distribution. This is a TM field distribution. This comes in, we will see later, in circular type of waveguides, not coaxial cable. That means, only one conductor is here. So, in a hollow metallic pipe, cylindrical pipe, you see electric field vector, it is like this. Also electric field vector we are showing in the any between thing at x is equal to 0, it has a longitudinal component. This is an example of a transverse magnetic mode. Now, consider another example, that instead of that line source, let us make a loop, infinite loop of current carrying I. So, consider an infinite loop. Obviously, the electric field will be azimuthal. You see, at every point electric field is, because it should be in the direction of this conduction current. There is a conduction current here. So, it is in the E phi direction, that is called azimuthal, and entirely lying in the z0 plane. You see here, E phi all are lying in the z is equal to 0 plane. So, the magnetic field vector should not be lying entirely in this plane. Why? Because then we are going back to the TM case. Again that same logic. So, magnetic vector should have a component in the transverse plane and also some component along the z direction. These waves are called TE modes. Their field distribution is like this. This comes in, we will see in waveguides. You are familiar with that it is a example of a T10 mode. This type of various modes, but all of them they have that you see in the transverse plane the electric field is lying. We are seeing in a longitudinal plane, you see it is basically the waveguide. Between that, if we can see, we will see that field distribution is like this. There is no component which is in the z direction. So, electric field is entirely in the transverse direction. And as I was saying that with mixing this type of various modes, you see 3 TMT type of electric field distribution, if they are mixed, then you get a field distribution like this. So, all these various things, but all are linear combinations of these modes. So, a particular field may be, suppose when in a coaxial line, transmission line, you can have all the modes possible, TM, T, TM, all the them can be possible. In waveguides you cannot have TM, and so if you see the actual field distribution, you will see something haphazard. But if you break it into these components, you will then understand that how much of T, how much of TM, and which type of T also have various with numbers. These two numbers, they are giving 2-dimensional modes. So, various numbers are possible. So, with that you get all the real life signals. So, if you understand modes, you can easily break the fields into these modes and then your analysis will proceed. So, that was our first lecture, that what is the concept of mode. I think I have tried to make you understand that there are 3 fundamental modes, TM, T and T0, and where from they come. We have given you examples that which type of sources can produce a pure of that variety. In real life you have a source which is mixture of all these various sources I have shown. So, with that they produce various types of TM, TE, T0. Now, we need a supporting structure which can carry that, so that energy will be coming from transmitter to receiver. That we will see one by one in the next lecture. Thank you.